The J-50, sometimes referred to as JXD or JXDS, is one of the most notable developments within China's advanced fighter aircraft programs. Although the designation is unofficial and not formally acknowledged by Chinese defense authorities, consistent external observations indicate that the program exists as a significant next-generation platform, likely aimed at shaping China's future air combat capabilities for the coming decades. The aircraft is under development by the Shenyang Aircraft Corporation, one of China's major aerospace firms, which has historically contributed to both licensed and indigenous fighter programs. Based on current assessments, the J-50's design, configuration, and apparent purpose position it as a crucial element in China's broader military technical trajectory, particularly in high-end airpower applications. The most striking element of the aircraft's design is its tailless configuration. Conventional fighters utilize vertical stabilizers for directional control and aerodynamic stability, particularly during yaw-intensive maneuvers and low-speed flight. The absence of such surfaces in the J-50 suggests a radical commitment to reducing radar cross-section from all angles, particularly side and rear aspects, where vertical fins tend to reflect radar energy. This move also reduces drag, which can be beneficial for sustained high-speed flight. However, it introduces significant engineering challenges, especially in flight control. Without vertical stabilizers, the aircraft must rely on advanced fly-by-wire systems, thrust vectoring, and other aerodynamic control surfaces, such as moving wingtips or flaperons, to maintain stability across the flight envelope. The aircraft's use of thrust vectoring nozzles implies that engine output can be directed at different angles to assist with pitch, roll, and yaw control. While thrust vectoring is not new, its use in a tailless configuration underscores the level of control software sophistication required to keep such an airframe stable and agile in dynamic conditions. This further indicates the platform is built around high levels of onboard computation, real-time sensor feedback, and precise mechanical coordination. For the aircraft to be combat viable with such a design, its flight control systems must manage not only normal flight dynamics, but also respond to unpredictable or degraded conditions, such as damage, turbulence, or extreme maneuvering, without the structural safety nets traditional tail fins provide. Another important element of the J-50 is its twin-engine layout. While engine specifics have not been confirmed, they are widely considered to be from the WS-10C family or a comparable domestic powerplant. The use of two engines offers redundancy and additional thrust, both necessary for supercruise, heavy payloads, and combat survivability. Supercruise, the ability to sustain supersonic flight without afterburners, is a key performance objective for many modern air superiority fighters. It reduces infrared signature, increases endurance, and enables a greater range of tactical options. For the J-50, a successful supercruise regime would mean it could penetrate defended airspace quickly, engage targets with minimal warning, and disengage before adversaries can effectively respond. The aircraft also appears to feature diverterless supersonic inlets. These are specialized air intake designs that eliminate the need for traditional boundary layer diverters, reducing mechanical complexity and surface features that reflect radar. The choice of diverterless intakes aligns with a stealth-first approach to design. Combined with the aircraft's overall smooth surface treatment, edge alignment, and likely internal weapons bays, the airframe is engineered to significantly reduce radar cross-section across a broad range of frequencies. In stealth design, shaping often plays a more dominant role than radar-absorbing materials, particularly for high-power surveillance and targeting radars. This aircraft's shaping indicates a design priority for wideband low observability, which suggests its mission set includes first-entry operations into defended airspace. The internal volume of the airframe is likely optimized to carry fuel and weapons while maintaining stealth. Internal bays are standard in stealth fighters because external stores severely degrade low observability. Observed design features suggest multiple internal weapons compartments, likely configured to hold short and medium-range air-to-air missiles and possibly precision air-to-ground munitions. The internal bay configuration also affects combat doctrine. Aircraft relying on stealth must maximize efficiency of engagement, neutralizing threats without prolonged exposure or requiring multiple passes. This makes sensor fusion and first-shot capability especially important. Sensor systems on the aircraft are assumed to be both passive and active. The nose likely houses a high-performance radar system, possibly an AESA radar. AESA systems allow for electronic beam steering, target tracking, and low probability of intercept, meaning the aircraft can scan the battlespace without revealing its own location. Additionally, infrared search and track (IRST) systems may be integrated for passive detection of heat sources. These are useful against stealthy or low-emission targets and are becoming a standard part of modern fighter sensor suites. The J-50 would also likely feature advanced electronic support measures to detect, classify, and respond to incoming radar signals from enemy aircraft or ground-based systems. Pilot integration is another critical element. The single-seat cockpit appears to be enclosed by a low-profile canopy, consistent with stealth priorities. While the reduced canopy size may limit direct visual range, modern cockpit designs emphasize sensor data fusion and synthetic visualization, where radar, infrared, and other sensor inputs are merged and displayed in a coherent format for the pilot. This reduces cognitive load and allows the pilot to focus on high-level decision-making rather than basic aircraft management. Voice commands, gesture recognition, and helmet-mounted displays may be integrated to support more fluid interaction between human and machine. The J-50 is likely intended to operate in coordination with other assets, manned and unmanned. China is pursuing advanced unmanned combat aircraft and loyal wingman concepts, autonomous or semi-autonomous drones that can fly alongside crewed aircraft, extending sensor range and carrying out support roles. In this ecosystem, the J-50 could serve as a control node, using its sensors and data links to manage operations over a wide area. This kind of distributed, networked combat structure increases survivability, lethality, and adaptability. The pilot would act less like a traditional dogfighter and more like a mission commander, orchestrating a complex set of tools and assets to achieve objectives under changing conditions. As for the intended missions of the aircraft, its configuration is clearly optimized for air superiority. It is built to detect, engage, and defeat opposing fighters in contested environments. Its speed, stealth, and sensor integration suggest it is meant to operate forward in high-risk zones where traditional aircraft would be vulnerable. Secondary missions may include precision strike, especially if munitions and targeting capabilities are developed for internal carriage. However, range and payload limitations, common to stealth fighters, mean it is best suited for high-value, short-duration engagements rather than long-endurance bombing or deep interdiction roles unless supported by tankers or external logistics. There are also indications that the J-50 may be part of a broader force structure that includes different classes of advanced fighters. In such a structure, the J-50 would be the more numerous, agile, frontline platform, working in conjunction with larger, longer-range fighters or bombers. This high-low mix allows operational flexibility, cost balancing, and resilience across different mission types. The concept echoes force structures used by other major powers, where lighter fighters are complemented by heavier, more specialized platforms for complex missions or strategic roles. Challenges remain. Chief among them is the maturity and reliability of the propulsion system. Chinese engine development has made visible progress, but long-term operational reliability, especially in high-performance regimes, is still an area under observation. Flight control software, sensor fusion systems, and network integration are also key hurdles. These systems must operate flawlessly under combat conditions, which requires extensive testing and refinement. The J-50 appears to be a carefully considered leap forward in Chinese military aviation. It is not a simple evolution of earlier fighters, but rather a rethinking of how future air combat will unfold. Data-driven, stealth-oriented, highly automated, and deeply integrated into networked battle management systems. Its development reflects strategic ambition, technical progress, and a clear intent to build an air force capable of operating in highly contested environments where survival, speed, and first strike ability determine outcomes. While much remains to be confirmed through time and testing, the aircraft already represents a substantial technological and conceptual shift in China's approach to future warfare.